Yep, I have shared the link of the notebook. Anybody wants to follow along, you can just open it in the Google Colab, and you can follow along. Yep.
Okay, thank you. Thank you, Sam. So we can start, Iman? Yeah,
Yeah, let's start. The recording has been started also.
yeah. Okay, okay, okay. So, hello everyone. Thank you for joining us. Today is our fifth workshop with our amazing speaker and content creator, Salman. So, Salman Khaliq is a machine learning engineering consultant and a certified TensorFlow developer. He also managed the biggest machine learning community on LinkedIn and creates content on both YouTube and LinkedIn. So thank you very much, Selman, for joining us. And please go ahead.
Yep. Thank you so much, Kara, for inviting me. Means I really like to be here. So, hi everyone. So, as Kara told you, that I usually do consultation projects. So, it's technically I'm a private contractor. I do not work for any company. I kind of like offer my services to different companies. I have worked with several different companies as a machine learning engineer, and I'm also managing one of the biggest machine learning community on LinkedIn, which is about 1.39 million people. So and I usually put some content on YouTube here and there, and previously I was also putting it on LinkedIn, but for a few months I was taking a break. Most probably I would start working on it again. This is kind of like me getting back to the routine again. So this particular workshop we would be doing is we would be learning how decision trees work, and we would be coding it from the scratch. Not just coding it, we would understand the mathematics or intuition behind it as well. So I would try to make it as compact as possible, so and give you enough detail so that you understand what we are doing. Other than that, because I don't want to extend this particular session to be pretty long, so, yep, we can get started. And I have already shared the link for the notebook that I would be using. If anybody wants to use it as I'm doing it, please open it in Google Colab. And if you have any questions during the session, please raise your hand. And I would address your questions once I am kind of like in the middle of explaining or talking about something. Once I finish that, I would get back to your question. So if you have any question, just raise your hand or just leave them in the comments, and I would read them and address them later. Yeah. So let me quickly share my screen. Okay. Uh, okay. So everybody can see my screen, right?
Yeah, we can see.
Okay, sounds good. So this is the notebook I was talking about. So it is kind of like it has almost everything on it. I try to put as much detail on it so that even if you are going through it again on your own, you have enough information, the descriptions and things like that. Maybe later I would update it, and there are some formulas missing which I wanted to show you by hand. So there are several different kind of like methods or models, you would say, that works behind the decision trees. I would be using just one of the model today, and not all of them, and I would not even talk about all the other ones. So first thing first, what I have done is I would be using this dummy data set. So this data set I just generated on my own. So what that data set is, basically it has about all these columns, and we have information about students. So this is excuse me. So this is student one. The age of the student is given. The GPA of the student is given. Whether the parents have approved that, whether they give permission for this particular student to attend athletics or not. It tells you whether yes or no. And then the physical form. So if you are working in a school, or if you are a teacher or anything, and you want consent from the parents about participating in any activity, you want them to sign a particular paper, so that legally it's not your liability if anything happens, because they know all the consequences and things like that. So they have kind of like a physical form, and if they have submitted that form or not, they have completed it or not. So that is this column. The last column is whether they would be participating or not. So what we have to do is we have to predict the participation depending on the data given. So this is just 7 data points, and we have a lot of columns, and we would be doing the decision trees first by hand. And don't want to use so many columns, because then our work would be so much more. So you would understand it way better with less number of columns. So what I am doing is I'm kind of like reducing the amount of data. So I'm just focusing on these 4 columns for now. So these 4 columns are age, parent approval, physical form, and participation. Participation is my target variable here. So participation is my target variable in this scenario, and age, parent approval, and physical form, these 3 columns are my features. And I would be predicting whether the student would participate in the physical activity or athletics or not, depending on what is the age of the student, whether the parents have given the approval or not, or whether they have submitted or completed the physical form or not. So let's go back to the notebook, because before we code it from scratch, we need to understand the algorithm behind it, how decision trees work. So if you think about decision trees are technically a way to filter your data. So technically what decision trees do is basically they start filtering. If you have ever watched a coin sorter, means if you put all different types of coins, for example, like if you put 1 cent, 5 cent, 10 cents, and $1 coins, what it does is basically the machine basically sorts out, it puts all the 1 cents in the column of the 1 cent, all the ones in the 5 cents, all the ones in the 25 cents, and so on. So it sorts it out. Decision trees work exactly the same way. How does that machine sorting or coin sorting machine works? Basically it works on, for example, like it has, you can say, means coins are passing through here. So this coin is passing, this coin is big, it's going to fall when the diameter is just enough so that the coin is going to fall. If the coin is small, it's going to fall in this particular column. If the coin is big, it's not going to be able to fall in this particular column, it's going to be able to fall maybe when it reaches somewhere here, then it's going to fall in this particular column. Decision trees work exactly the same way. What we do is we basically want to figure out what is the participation rate. Now there are so many columns. Right now I'm not considering this column. So this column is cancelled out. I'm not considering it. This column is also cancelled out because this one has floats. Right now I don't want to deal with the floats. I'm focusing on age and parent approval and physical form. These are the 3 features on which basis I would be predicting whether the student would be participating or not. First thing the decision trees do is they start with a question. The question is, there are so many different possible questions in this scenario. The one of the question you can see, look at the age. If you look at the age, you can see that 14, 15, and 16. These are 3 different possible ages I have: 14, 15, and 16. What I can do is I can ask a question. I can select all the rows when my age value is greater than or equals to 14, or I can predict when it is greater than or equals to 15, or I can take all the rows when the values are greater than or equals to 16, and look at what is the participation rate for them. All the values which are greater than 14, technically greater than 14 makes this 15 is also part of it, 16 is also part of it. So if I'm considering all the cases when the value of age is greater than 14, technically what I'm talking about all of these cases. So this using this question would not be a good idea because here I'm considering all the available data. If I do greater than 15, so greater than 15 would give me how many possible values. You can see over here, why I cannot see my, so you can see over here, this is 15, and then this is 15, and that's it. There are only two rows on which I have kind of like the the age is 15. You can see when the age is 15, one thing is pretty sure that the participation rate is no. That means one of the question that I can ask is that if the age is greater than 0, then I can get two no's and rest of them would be on this side, which means I can start with the node. That node would be a question, and that question is all the possible values when the value is greater than and equals to 15. What it would do is it would check for all the values whether this condition is met somewhere or not. So you can see if it is greater than and equals to, that means the values 16 are also part of it. That means only the 14 would be excluded. That means it is not still a good division of the data. Just give me a second because for some reason I cannot uh, see my cursor. Let me copy the data. Yes, I think now I should see it. So what I'm saying is this is 15. So greater than equals to 15. This is one of the equation. I'm picking all the rows in my data when the age value is greater than and equals to 15, which means this 15 is part of it. This 16 is also part of it. This 15 is part of it. This 16. That means these four rows I would be picking. If I divide my data based on this, that means everything above it and equals to it would be on one side. So if it meets this condition, I would put it here. That means you will pick these four rows and put them here. So this is row 1, row 2, row 3, and row 4. The remaining two rows, this one and this one and this one, the three rows, you're going to put here. The rows which start with 14. The rows which start with 15 and 16 are going to be here. And then you're going to count how many times you got yes and no in this column, your prediction column. So you can see that if I use this particular equation, I cannot, or I am not getting 100% filtered result. So let's count the number of yes and no's I am getting. So look at this one. This one is giving me no. Look at this particular row. This row is giving me yes. Look at this particular row. This row is giving me no. And look at this particular row. This row is giving me no. So I have three no's, 1, 2, 3, and I have one yes. That means on this side, I was not able to separate yes and no completely. The goal here is you need to ask the right question which can divide your or purify your kind of like output. That means on one side you get 100% pure yes or no, and on the other side maybe you can have mixed of them, and then you can keep on dividing them again and again until you get the purified form. So the quicker you would get it, the faster you would get it, the better your model is going to be, because you want an efficient model, right? So which works really fast. You don't want it to try all the questions and every single time. So you want it to try all the questions one time and figure out which is the best question to ask. And based on that, just train itself on that particular question. And then every single time you ask the next question, that means you are doing a prediction, it will only go and look for that particular question and will give you the answer right away. So over here you can see the purification is still not on kind of like 100%. On this particular line, I can see I have a yes. On this particular line, I have a no. On this this particular line, I have a yes. That means on both sides, I was not able to purify either one of the sides. The goal is to purify both the sides eventually. But here I'm getting some mixed yes and no. I'm getting some mixed yes and no. That means this is still not a good question to ask. One of the good questions to ask in this scenario, you can see that this missing value. If means I have taught for a while. And I know that this is something. For example, like because teachers don't want to be liable on anything, so which means whenever there is a responsibility kind of thing, they do get assigned consent from their guardians, students, guardians, and parents, and things like that. Which means if this physical form is considered to be something which everybody needs to submit in order to take part in athletics, you can see if this form is missing, I'm not going to allow the student to take part in athletics, because if something happens, that's on me, and I'm not going to take that responsibility. And you can see that both missing are giving me the result no. That means I was only looking at this column. If none of these values would be giving me a pure answer, I would go for the next column, the parent approval, or the GPA, or the physical form. I would try all the possible questions here and see which questions can give me a purified answer, at least on one side, if not on both sides. So you can see if I go on this column, and in this column I have two values, whether the form is complete or missing, which means I can see if it is missing, then I get 100% no. That means if I am giving you another data point, let's say there is another student whose age is 14 years old, whose GPA is really good, 4.0 GPA. Parents have given them the permission, but they have not submitted the form. What's going to happen is this student going to take part in the athletic session or not? That student is not going to take part, because based on my data I can see that whenever this form is missing, the student cannot participate. It's as simple as that. If I had some other thing, for example, if I had this form completed, then I would have to take a look at some other things. But if this thing is missing, I don't care about any other value. If it is missing in this particular data, missing means no. So that means missing should be a good starting point in this scenario. So when I say good starting point, that means I should ask a question whether the physical form is missing or not. So if I'm asking a question whether the physical form, so I would use the short form physical form is missing or not. That would be my the first root node or first question I should ask. Then I should write all the values which are either yes or no. So write all the rows. So look at all the rows. Let me erase, clean up the data, and let's use it all over again. Since this one did not work, I'm erasing it. Okay. So I don't want a lot of things to get messed up. Now, if I'm using this as my question, then what I would do, I would go for find all the missing values, which means I will pick up this row. This row is telling me that when the form is missing, and this row is also telling me when the form is missing. So which means I have when the age is 14, I get the GPA is 3.9, the parent approval is yes, and the first physical form is missing, and I get a no for the participation. Same with this particular data set that you can see the age is 15, the GPA is 2.5, parents have not given the approval, and the form is also missing, which means this student is also gonna do. And you can see there were only two cases in my data set. And over here, I get 100% no. 100% no means a purified division of my data. That means I got 100% no's over there. So one of the section is already purified. The goal in decision trees is keeps on asking question, and every question should purify your data. It's kind of like a lot of filters you are applying. Every question is a filter. You ask the right question, that would be the right filter, which would be able to purify or filter out most of the garbage or most of the randomness in the data. So What I did is I basically filtered out a lot of randomness in my data, and here I got zero randomness. I have 100% no. So that is the goal over here. On the yes part, I would get all the remaining other. For example, this particular row, let me change the size. You can see this particular row, and then this particular row, and then this particular row, and this particular row. All of these rows are going to be here. And now I'm going to do is I will count how many of yes I get on this side and how many of um, 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 no's I get. So I can see I get one yes, I get one no, then I get another yes, then I get another yes, and then I get another no. So which means I'm getting mixed answers here. But one side is 100% purified, which means this is a good question to ask at the start. So this particular starting question, from where I can start and I can purify most of at least one of the leaf or branch, you can say, since we are talking about trees. So now let's talk in terms of trees. So tree originate from a root, right? So this first question is what we call the root node. So this is our root node. These are two branches extending out of it. This branch is 100% purified. If it is 100% purified, we call it the leaf node. This particular branch is not purified yet, so I would still call it the branch. I would still not call it anything else. What I'm going to do is I'm going to further divide this branch into further two kind of like. Now I would ask questions. So I did ask about physical form being missing. That was my question. Maybe I would ask about if it is complete or not. So the thing is, over here it is complete, over here it is missing. I have already divided it based on that. Now what I can do is I can maybe go to parents approval. You can see when the parents have approved and this is complete, you get a yes. When the parents have a no, you can see a no here. When the parents have a yes, we have a yes here. And when the parents have a yes here, we have a yes here. This case is a different one, which would make your division a little bit tricky over here. So you would have to try all possibilities. Maybe you would look for age. So you have to ask the right question. And you can see that in this particular data set, there are so many different questions you can ask. Now, let me show you using the code that how many questions you can ask. And remember, I'm using in this particular scenario a small data, means I'm just using these columns. I'm not using all the columns. Based on these columns, if I train, so I just um, so let it initiate. So I just this is the data set I just put in here, and these are the names of the features and everything. Let's implement the decision tree. Let me show you. So what I'm doing over here is I just wrote a helper function here. This helper function is doing what? It is creating the questions. How many questions can I ask here? So the questions are the number of possible. So questions are, how many unique terms or unique values do you have in this column? We have 3 unique values. How many unique values do you have in this column? 3.5. So there are several different. Since we are not considering this column, let's erase it. How many unique values do you have here? Yes and no, two different unique values. How many unique values do you have here? You have two unique values. That means how many possible questions you can ask? You can ask 3 plus 2, 5, 5 plus 2, 7. That means there are 7 possible questions that you can ask. That means the decision tree will try all 7 questions at the first attempt and see which one can purify the results quickly, can give you at least one of the leaf node. So this one is a leaf node, this one is not, which means when it can purify completely, you get a leaf node. When you cannot, you do not get a leaf node. You get 2 branches. So since here I'm getting a leaf node, that means this is a good question to ask. Now, how do we determine which question would give you the best result? Here, my data was pretty small, and I could see, and I used some domain specific knowledge here to ask the right question and save myself some time. But machines, if I'm giving them thousands of data points, then I cannot do it just by looking at it. We need a way to get this all the process done mathematically somehow. So that's where some different types of algorithms come into play. What they do is they measure how much impurity is remaining in a leaf node or in a branch. So what they do is they basically measure the impurity at the start, and then they measure the impurity if you divide based on a particular question. So we can ask three questions using all the values in this column, we can ask two questions using all the values in this column, and we can ask two questions here. That means for every question you would measure the impurity of the root node and the two emerging dotted nodes and see how much impurity you were able to get rid of. The more impurity you were able to get rid of, the better your question would be. And that is what is the algorithm that we use in the background. So there is a mathematical thing, we call it Gini index. We calculate Gini index. What is Gini index? Gini index is simply the amount of this index, or this number tells you the amount of impurity in your data. So this tells you amount of impurity in your data. Now, the formula for the Gini index is pretty simple. If I write it right now, don't get confused. What are these values? I would explain it. What we do is we basically subtract the probability of each individual possibility. For example, this was my question that the parent or the physical form was missing. If you look here, that means before I do anything, I have to calculate the original given impurity. What is the original given impurity? Is the probability, or how many out of total are yeses and how many out of total are nos. So you can see there are 7 data points here. How many yes do you see? One, two, three. There are three yeses. So which means there are 7 data points. What is the probability of getting a yes here? 3 out of 7. What we do is we square this value. So 1 minus, that means whatever the probability you get here, you subtract it from 1. And also the probability of no as well. What is the probability of no? We have 4 no's here. So that means the probability of getting a no is 4 over 7. And you do a square of here. So when you simplify it, you would get a number. And this is what we call the amount of impurity my original data had. We call it Gini index. You just figure out the Gini index or value of the Gini index for the original complete sample of your data. Okay. So when you simplify it, if you put it in your calculator, you would get a number. I think you get 0.4897. Correct me if I'm wrong. I think I'm getting this 0.4897. So 97. So this is the value I'm getting right now. That means this is the Gini index or the original impurity in my data. Now every single time you divide your or filter out some of the data, you will get less amount of impurity. Yeah, that means the amount of impurity is going to go down. So how much impurity is going down? We call that part information gain. Information gain is simply how much impurity you lose when you ask a question and divide it into two branches. By doing that, how much impurity you end up losing in that scenario. This is what we call the information gain. That means how much of the purity you gained. That's another way to say it. So information gain is technically how much purity you gained or how much pure your data become as compared to the last time. So the more it's gonna become pure, the better it's gonna be. So what we do is we ask all these 7 questions. So which 7 question? 3 from this column, 2 from this column, and 2 from this column. And then we calculate the Gini index from all of those columns. And then we see how it divides after asking that question. And then we calculate the Gini index again after the division and subtract from the original value. The number you get is the information gain that you're calculating. Whatever number gives you the bigger value, that is the question you should ask first. So that's how decision trees work. Now let's calculate all or do all the calculations for at least one of the question so that we know what we are doing. Okay. And then at the end, I would give you a sample data, or maybe you can use the whole data set that I have provided you. I had given you more columns, so you can try all the other columns that I'm not considering right now. Okay. So now, one thing, so far, anybody has any questions?
Yes, I want to ask something.
Yep, sure.
Okay, so you did tell us that each node is supposed to be a question,
Mm-hmm,
and based on what answer we'd be getting from each question, they would be
mm-hmm.
divided to other leaf nodes, right?
Yep.
So, is there any convention of like this side is supposed to be the true answers, or is there any conventions that we have to look out for when creating or distributing the nodes?
The only convention is this Gini index, and then there is another thing which we use, entropy. The only thing they do is the formula is slightly different. Other than that, you do the same steps every single time. However many columns you have, you find the unique values in every column and add them up. That many questions you ask in the beginning, and once you ask those questions, you divide based on those questions and calculate the impurity and see how much impurity you lose after you divide your data. So the more impurity you lose, that means the more pure you are getting, or more kind of like purity you are getting. The more purity you are getting, that question is giving you more information, which means you would be able to purify your data quickly based on that particular value, because that is the only thing that you have to ask. You divide the number of questions and then calculate the Gini index of every single question, and then divide based on that and compare. And whichever is giving you more information gain, that is the first question you should ask. Same way, when you go to the next node, you do the same thing. Then you go to the next node, you do the same thing. So this kind of like, it is a recursive process. Same thing over and over and over again for every single node. Does that make sense?
Okay,
Does that
yeah,
answer
yeah,
your question?
yeah. Thank you.
Hmm. Yep. Um, okay. So I just wanted to see that if anybody is confused on anything. So even if anybody has any confusion, please ask me. Now what I'm gonna do is I would show you at least one node and calculations for one of the node, so that we understand what we are doing. So here, what I did is I calculated the Gini value. So this is the Gini value of the total sample. Now what I would be doing is I have 7 questions to ask. So I will not show you calculations for all 7 questions. I would show you calculation for one of the question. You can try practicing for calculating for all 7 questions and see what you get. And when I'm coding, I will show you the results automatically, because while coding I just have to write few lines of code and I can show you those numbers very quickly. And now, for example, like if you go on the code, I have already done that. So for example, right now I would explain this code, but if you don't understand it, don't worry about it, I will explain it here. um, so all these functions, you can see these are the questions I should be asking. We had 7 questions: whether the age is greater than equals to 16, greater than equals to 14, greater than equals to 15. These were the 3 different values in the age column. Then the parent approval column had 2 values, yes and no, which means I'm asking whether the parent approval is no or yes. The other two questions are physical form, whether it was completed or missing. So these are the 7 questions. First thing, you figure out the number of questions. Second thing, you figure out the Gini index for all of these questions. So that is, let me show you just the values. I will talk about the code as well. So uh, we should have some result. You can see that this was question number 1. If I start with whether age is greater than or equals to 16, based on that, gene impurity of the true branch. So you will get 2 branches, a true and false, or yes and no. True branch gives you this impurity, this Gini index, and the false branch gives you this, and the information gain that you're getting. So technically, you can see this number is 0.5, and if we go back to our over here, this value is 0.4897. You subtract zero point 0.5 from it, you see how much change you got, and that change is the information gain over here that is being calculated. So this is 0.041. Same for this particular question, same for this particular question, all these 7 questions. You can see the one where the parent approve, the physical form is missing, we are getting the most amount of information gain, 0.2755. So this 0.2755 is the biggest amount of information gain we are getting out of all the possible 7 questions, which means my first root node should be this particular node. And I would divide my data based on that. Okay. So let's go back and let's calculate it for that. So this is the total sample. Now what I'm going to be doing is I'm going to be calculating the Gini value if my question is based on. So I would call this as Gini of the total sample. So now I would be calculating based on sample, and in this scenario my data is uh, the missing value. So I'm calculating based on missing value, or I would call it the physical form. Okay. Now, how do we calculate it? It's pretty straightforward. You have to figure out the weighted percentage. So let me write down the numbers. You would understand what I'm talking about. I have done few calculations, so that would save us some time. So for example, like what I would be doing is I would be dividing my data based on this particular question. So in fact, let me rewrite this data over here because I have to use it again. So this is the data set that we have. Now, what I would be doing is, first thing first, I would be dividing based on missing value. That means these two values I would write. So based on physical form, let's say, so physical form gives me two values. Either it can give you complete or it can give you missing. What I'm doing is I'm calculating how many complete and how many missing. And out of these complete, tell me how many of them are telling you yes. So I can see one of the yes here. Then this one is completed is telling me no. So let's count the number of yes and number of no's. So I can see I get one of the yes here. Then I get one of the no. Then I get for this complete another yes. Then another complete another yes. Okay, so which means I got 3 yeses and 1 no's. So let's summarize it. So this is 3 yeses and 1 no's. For missing, I get 1 and 2 no's. 3 no's. And no yeses. Which means now what I would be doing, you can see how many total possible cases I'm getting when the form was completed. 3 plus 1 is 4 times when this was happening. How many times it was missing? 0 plus 3 would give me total 3 times. That means this gives me total of 7 possible options. Now, the thing is, when I'm calculating impurity based on the number of complete and missing and things like that, what we do is we basically, the notation is you write the Gini and then it is based on the subsample. So you are comparing it with the subsample. That's how you would be getting the information gain. And then you're comparing it with the physical form. What you do is you figure out the weighted or weight of the missing values and weight of the complete values, and then find the Gini using the same formula that we have learned. So what is the weight of the missing values are technically over here we are getting. So missing values, we have total 3 out of 7. So that is the weight of the missing values. And then I will calculate the Gini value of it. So remember the formula for the Gini value. The Gini value formula is simply 1 minus the probability of yeses and minus the probability of nos. Over here, I would go and I would find 1 minus what is the probability of yeses for the missing? It is 0 over 7 square. Then I will figure out the probability of no's, which is 3 over 7 square, and so on. Right? So we can calculate based on that. Am I doing something wrong? No. I think I'm doing. We should be getting a 0 here. I think I missed something. Okay, let me double check.
Yes,
Sir,
Salman, please. I think Amir would like to talk. Yes, please go ahead, Amir. It was you.
sir, I guess 3 over 3 and 0 over 3, not over 7.
Oh yes, yes, yes. Yep, that's right. So because we have total of 3, I'm considering 7. That's what. So it should be 0 over 3, and it is 3 over 3. Yeah, because we should be getting a 0 here, and I was just making sure that we should be getting. So we would be getting a 0 here. We would be getting a 1 here, and 1 minus 1 would give me 0. So this whole bracket is going to be 0. And then what I would be doing is I would be adding the Gini value or weighted sum of the completeness. So that would be, remember, we are getting 2 branches. I would be calculating the Gini value for this branch, and I would be calculating the Gini value for this branch. So what I did is I basically calculated the Gini value of when it was missing. A missing value was, you can say, yes, and when the missing value was no technically. So I'm calculating this and this, both of them. I've already calculated this one. This would end up being 0 because the it would give you all no's. That means it is 100% purified. There should be not any impurity. And over here we should get some impurity, and let's do that. For that, the weight is 4 over 7 for the second part, for the complete part. And then we would subtract 1 minus the probability of yeses, which is 3 over 4. So it would be 3 divided by 4 whole square minus, and then it would be 1 divided by 4 whole square. When we simplify this whole thing is already 0. When you simplify this, you would get a number. Whatever number you get, what you would do is you would go back and you would subtract that number from here. So whatever Gini value you are getting for this particular section, s comma physical form, you subtract it, and whatever number you get, that is what we call the information gain. So I just wanted to show you one of them. Now what you can do is you can do it based on any of the other node. And remember, over here you would get 2 nodes. So this one is 100% purified. Now this node, you have to do the same process all over again. Keep on dividing the rows, and then until you get the 2 leaves. If you don't get the 2 leaves, you keep on dividing, or maybe you would have a restriction in your model that you cannot go beyond a certain number of divisions, or the number of leaves are limited, or things like that. So there are minimum leaf count or something like that. Okay, so this is the whole process. Now let me go to the code part and let me show you all of these steps one by one. So if I go to the notebook, let's start from the top. The very first function that I have written. So this is the data set that I was using. I'm using the same data set. And then what I'm doing is I wrote a helper function which extract all the possible questions. What it does is basically it goes to every single column of my data set. So technically, the last column is my target column. Rest of the other columns are my feature column. So it will go to all the feature columns, find the unique values, and whatever the unique value is, that would be a question that I can ask. So what I did is I basically converted that question in this form so that I can read the question, or it is in a readable form. What it is doing is it is finding the one of the unique value in one of the column, then writing the condition whether it is equal to or greater than or equals to. So if it is a text value, then I would be using equal to. For example, over here you can see I'm using equal to compare text values, and if these are numbers, then I'm using either greater than or equals to. I don't want to use exact numbers because sometimes you can have integers or floats or something like that. So if you don't use this, then there would be so many different divisions you would have to do, or you would be asking so many questions. So you can see that decision trees can be used for the regression problems as well. So which means this particular code that I'm writing, it would work for both regression and classification. Doesn't necessarily have to be classification. Okay, so which means if we have regression columns or numerical columns, integer or float or anything, this particular code should be able to handle it. So what I did is basically this particular class, question class, would separate all the questions and put them in the right order so that I can read them. Now, next thing what I would be doing is I would be identifying. So this is the class which is kind of like I'm calling and putting in a kind of like a structured way. But now this is the function I'm using to find all the unique values. What it is doing, it is going to my data set, looking at column number one and finding all the unique. Remember, one of the basic data structure in Python is sets. And the unique thing about set is you cannot put the same value more than once. So set always take, if you have hundreds of values which are repeated, for example, like if you have 3 comma 3 comma 3 in a list and you convert it into a set, you will get that just one 3 back. That means if 3 is repeated 3 times, set only gives you, it does not give you repeated values. So what I'm doing is I'm using sets to get rid of all the repetitions. That means I'm getting all the unique values. You can use np.unique here if you want to, but I'm using set here. It is going through all the different rows and gathering all the rows that we can get. Next thing, formulating the possible equation. So I'm asking all the possible questions. So technically, I'm making my questions. So those comparisons, whether the first unique value in column number one is equals to yes or no. So I'm gathering their or grabbing their values as well. So if it was yes or no, if my age was 14 or 15 or 16 or no. So I'm comparing those values with the unique values. Now, next thing I'm doing is extracting and displaying all possible questions. So these are all possible questions. So I'm using the previous all the question class and the two functions that I created all together, and I'm now generating all the questions. In the decision trees, this is how the things happen. Step number one, get all the questions. Step number two, now start calculating the Gini index. Okay, so this is what we would be doing. So evaluating splits in the decision tree, how do we do that? We count the number of classes. So this is what we do on the paper here. Count the number of classes means the calculation that I did over here, this part, this calculation is what this particular function is doing. This function is calculating all the possible count of classes in the respective, depending on the questions, how many classes you are getting, depending on the question. So you are counting them. So then calculating the Gini impurity. So over here, I'm calculating the Gini impurity using the formula. You can see I am using the same formula, probability of the label square. And I am subtracting it means depending on the label. So if I have two labels, I would subtract it two times. If I have three labels available, it would subtract three times. If I have four available, I would subtract it four. For example, like in my target column, I didn't only have yes and no. Maybe we were dealing with a question in which we have multiple classes, not just binary classes. I would be able to address it using this particular code. So it is just subtracting it. So I started with one and I keep on subtracting the next one and the next one depending on how many labels I have. So I'm running the for loop here. So if I run it, this function would be able to calculate the impurity. Once I get the impurity, then what I can do is I can do the partition. How? By calculating the information gain. So when I run this partition, it basically creates how many would go on the true side and how many would go on the false side. So you would divide your tree or root into two branches. So this partition is gonna send all the rows which are on one side, put them on the right side, true side, and all the other ones on the false side. So then this is the information gain. You can see this is what we did. We calculated the p-value. P-value was the weighted value of that particular label, yes or no. So, and this is the same formula that we implemented over here. I was subtracting 1 minus, so this 4 over 7 was the weight, this p-value, and you calculate the other p-value. So it's pretty simple since we only had two labels over here. So what I did is basically 3 over 7 and 4 over 7. I could have used the other way around, but I wanted to kind of like address this based on that, so I did that. 1 minus p. If we had more than one classes, then this particular function is only limited to two classes. If it is more than two classes, this function is going to give you bad results, okay, not accurate results, because I'm not considering all the probabilities. I'm just considering binary case here. So maybe I did not think it through when I was doing that. So but still it would give us this answer. So let's do that. Now, finding the best split. Now, how to find the best split? Find the information gain and see which one is the biggest information gain. And that question is what we would start with. So this particular code is doing the same thing. So first I'm running the for loop one time. That means go to all the columns, extract all the values for each unique values in the column. Then for every single value, calculate the gene impurity, and then calculate the information gain as well and see which one gets. So and keep on recording all those values, and finally I will compare it. The best one I would display it. So once I get the best one, so let's see, if I run it, I would get this. So question number one gave me this, question number two gave me this, question number three gave me this. You can see the Gini impurity is also given of the right branch or the left branch, both of them. And final information gain is given. You can see this one is pretty small. This one is pretty small. This one is 0.1469. It's good. Zero point 0.1. These two branches have exactly the same Gini impurity. In some situations in reality, you would get the first node to have multiple questions can give you the same amount of information gain. Over here, if this was not giving you, this was not the case, I would have picked any one of them. Okay, so if they are same, then you would pick with anyone, and it picks usually the first one. So whatever is the first one over here, we got 0.2755. You can see it is repeated over here. Whether it is missing or complete, both of them would give you exactly the same answer, because if missing is giving you 100% right answer, complete is also giving you 100% right answer. You can see the information gain is being calculated here. So amount of impurity, impurity of false branch, and everything. So once we implemented that, now what I need to do is building and visualizing the decision tree. So we kind of like developed a decision tree. Let's run it for every single node, and we get a complete tree out of it. Okay, so right now what I showed you is just one node. It can have multiple of nodes. That means it can have several different leaves, because one of the leaf was 100% purified, the other one was not. I have to run the same algorithm for the next node as well, and I will keep on doing that until I'm satisfied, or overfitting is a thing that we need to be very careful about. But right now we don't care about it because we are dealing with very small amount of data set, and overfitting would be there. So we cannot avoid that. Now, over here, what I'm doing is I'm defining which particular node would be called. So now I divided my data into left and right. Which one would I call a leaf node? So this particular thing is just based on that. Based on the number of class counts and rows, I'm determining that. Okay. Then which one would be called the decision node? So a decision node asks a question. That means the node on which I will ask the next question, so that I get another division, because I don't get the 100% purified results here. So over here, I'm kind of like just defining all the values. I'm picking up all the previous values. Now, here I'm building the tree. What I'm doing over here is step number one, determine the best question. That is what I'm doing. So the base case, no further information gain. That is, since we can ask no further question, we will return a leaf. That means if your gain is 0, you say this is a leaf. If your impurity is 0, that means you would say that's a leaf. If it is not a leaf, then you move on to the next one. You figure out true and false values, then you figure out true branch and left false branch, yeah, yes branch and no branch, and finally you would call this as a decision node, and then you would run the same whole thing all over again. So let me run this. Now let's visualize this whole tree, the whole tree. So if I print this tree, the tree would look something like this. You see, question number 1, if I divide it, what happened? So you can see first question, it gave you something like this. I think it just printed out the same thing all over again. Yes, it is the tree. So this final thing is the tree. Rest of them word giving you information for every single node that you are creating. Okay. So over here, you can see the first division is the physical form complete or not? Based on that, I started dividing it. My Guinea value at that time was 0.489975. When we calculated manually, it was 0.48975. And here we are getting exactly the same thing. Information gain, when we calculated, it was 0.2755. So it is coming here. So it was true. So is parent approval? No. That is the second division that you are getting. So if it is true, then you are getting kind of like multiple, or you're getting an impure data set. And finally here. So let me copy this and let me show you what kind of a tree we are getting based on that. Okay, so over here, if I copy this information is telling you that your decision tree looks something like this. Your first question is whether it is complete or not, complete or missing, whatever. Then you get two branches. One of the branches is if it is complete, yes or no. So you can see if it is true, on the yes part, I'm getting something where I'm getting this Gini index and this information gain and this Gini value. How many true values you are getting? Um, uh, 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 and how many yes values you are getting and how many no values you are getting? 3 and 1. So which means you are getting 3 yeses and you are getting 1 no here. And over here, you are getting what? When it is false, you're getting all 3 no's. 3. So that is my first division. The next division is based on this. If it was yes and no, which means over here it is telling you that how many are yes and how many are no. So I getting all those numbers and those values are written over here. So if it was true, so is the parent approval? No. So which means if the parent, so over here I'm talking about parent approval now. So parent approval, if it is no or not. If it is no, then you are getting one prediction, no is 1. And if it is false, then you are getting 3 here, and so on. So you are getting all the complete answers. So if this cannot answer completely, then you get to the parent approval. And if parent approval cannot get you the answer, then you go to some other value. But over here, these two values would be enough. That means the age column is not doing anything at all. Age column is not being used whatsoever. And if you ever have heard about that the decision trees or all the tree models, they have the capability of figuring out the feature importance as well. What is the feature importance? It tells you which of the features are more important in predicting the values, final answers, the target, as compared to the other. You can see whether the physical form has been submitted or not has the most importance here. The second one is the parent approval. The one which doesn't even have any importance is the age of the student. We don't care about what the age is. We look at the parents permission, and we look at the form submissions. If the forms are not submitted, straight away, if it is not submitted, you cannot take part in athletic. If it is submitted, then we look at whether parents have given the consent or not. If parents have not given the consent, you cannot take part in it. So age does not take any part in it, which means the maybe GPA would take any part or not, because since I did not include it, you can try it and you can see if you would get something like that. So what I would do is I would recommend you to go on, use this notebook and copy the remaining column on this notebook as well. So come here and change the data set here. So here I put only 4 columns. You fill in the rest of the values from the other columns as well and see what kind of a tree you get. Okay, so I would recommend you to do that. So we build the tree and we visualize the tree. So we have the tree now. What we can do is we can put it all together and let's see the tree. So we already got the tree and we have already seen that. Next thing, let's use this tree and compare it with the scikit-learn's implementation. Okay, so before I do that, you can see I have written so many functions here, right? I have written multiple classes here. But if you're doing Python programming, you know that you can do you can create a one big decision tree class, and you can put all those functions in that one class, and you can all put all the classes that you have seen. You can make a multi classes and things like that. And this is what I did. I picked up all my code and make one big class in which we can do just like scikit-learns. You import decision tree, then run dot fit, and you fit the tree. And if you do dot predict, it's going to predict the results and things like that. So it would be able to do all those things. So what I did is I basically combined all those functions, the question class, all those methods in it, then the leaf class, then the decision node, all these classes I previously created, and then all the different methods that I'm using, and all the different functions that I'm using. And finally, I also added, so the build tree function, the print tree function, everything we have done. The only thing that I added here is the classify part. This is the predict part. I wanted to use different terminology. Scikit-learn use your model dot predict in order to predict your values. We should be able to predict unknown values, right? The test data as well. So I want to make the classify model as well. And keep one thing in mind, scikit-learn use fit method, but over here we don't have a fit method, we have a train method here. Okay, so we will use dot train over here in order to get the results done. Okay, so let me run this cell. So we have a complete working class now. Now let's compare it with scikit-learn. What I'm doing is I'm importing the iris flower data set. It is a very good data set, very small, 150 cases only, and very good data set to do classification or show you different classification. I don't want to use big data set because our model is not advanced enough to handle every single kind of scenario. So I wanted to keep it simple. The thing is, the whole idea of this particular workshop or this notebook was to give you a background intuition that how decision trees are working. Okay, so and break down the code in step by step way. Once you understand that, then put it all together, then you would understand. If I just gave you the complete code, the complete class, you would be thinking that what this part is doing, that part is doing. So I have shown you step by step. Hopefully that would make sense. So I just importing data, the iris data set from the dataset API here. Then I'm using the train test split. So I would be splitting my data set. I'm also getting this metric accuracy score for classification. And this is the decision tree classifier from the scikit-learn, which I would use for comparison. And you would see our model is going to work better than scikit-learn's implementation. So scikit-learn is going to give us 93% accuracy, and we will be getting 97.6% accuracy based on our model. So what I did is I did not run something. Okay, so let's see. Tree.train. Did I not put the train? It is train. This is my function. Okay, let's read. List index out of range. Okay, so train rows. It was working just now, because if you go, maybe let's go from here. Okay, I don't know what that is. What is happening here? So it was working previously. I would be getting this kind of a result. I don't know what that is. Why is this shaking like this? Maybe, yeah, the size is too big, I think. Okay, size is too big. So it was working fine previously, so I would troubleshoot it. Means I don't want to do that right now. But when you compare it, when you run this code, it should give you the answer. Most probably, I did not run any of the code somewhere in the back, maybe, or maybe I would have to restart the kernel. Then it would do that. Then I would have to run all the code again, which I don't want to do it. But you would end up getting the complete tree over here. This is the complete tree you would get from our model. And you can see over here the accuracy. Our accuracy is 97.76%, and the scikit-learn's decision tree accuracy is 93.33%. This is the tree that we are getting. Obviously, I did not create it like this. Means we have a complete we can use matplotlib library or plot underscore tree function from scikit-learn, and we can get a very good graph with all that information. But all that information that you see over here from the scikit-learn's implementation, I have given you in the text form over here. You can create that kind of a tree yourself, because all the values are already given here. You keep on creating two branches. So this is true, and when you get a false, you get two branches. So this false would be the first branch, this true would be the first branch, and this true would further divide. And similarly on the other side, it would keep on dividing based on that. Okay, so and you can see that, compare both of them. What are the Gini? So over here you can see it is starting at petal length 2.45, but we are starting at petal length 1.6. So we are starting at a different value. So they're starting at 2.45. So our model is doing maybe something different, and it figured out that the impurity index is different. And keep one thing in mind: decision tree, I'm using the base implementation, which means all the different parameters inside it are the default one, which means the model that I created, the from the scratch one, I did not even put so many different variables in it, because I wanted to show you how it works. We can make it more complicated by adding so much detail, like the minimum number of leaf nodes, or we can add the maximum depth or things like that. So if you go to scikit-learn decision tree, scikit-learn decision tree. So these are decision trees. So you can see the criteria we are using is Gini, and by default it was Gini. So we were good in that. The splitter, they were using best. We were also using the best one, not the random one. Maximum depth is something which originally was none. So we were good with that. But minimum sample split is 2. We were also good in that. That means these 4 things were kind of like same for us. Minimum sample leaf was 1. So we were also good with that. So some of the, for example, like minimum weight fraction leaf, they were taking it 0. but we were doing the weighted average, right? So that weighted average maybe changed our answer, and we got a better result based on that. So maximum features, since we had very few features, we don't care about it. But originally it is none, so that was fine as well. So most probably random state is another thing. I'm using random state 42, I think, over here. If you change the random state, most probably it's going to change your results as well. It should work. Okay, I would double check it. But if you download it from Google Colab, it should work, because my when no, from the GitHub, it should work, but for now it's not working. Yes, I did use random state 42. If you change the random state, most probably it's going to change the answer. So you can see that all these things are different. So maximum leaf nodes, originally we have none. Minimum impurity decrease is 0. All these things we can add into our own code, and we can make a complete scikit-learn comparison version of it, with all the different parameters, do hyperparameter tuning on things like that. But if you code it yourself, you would have so much flexibility that you can deal with. It's a good way to kind of like learn the algorithms. It's a good way to practice your Python skills as well. Coding from scratch, obviously it's also going to help you answering interview questions, because interviewers ask you what is your favorite algorithm or things like that. And the reason is they are asking you this question because once you tell them that you like this algorithm or that algorithm or whatever is your favorite one, they're going to go deep and ask you more questions about it. That why do you use this parameter, why, what happens in that, what is Gini index, means why do you use Gini index, and things like that. What is important information gain or things like that. So you would be able to understand better how decision trees work and answer a lot of different questions. Obviously this is kind of like decision trees, but how they're used in gradient boosting, how they're used in bagging methods, and extreme gradient boost takes it to a next level, and things like that. So there are so many different things that can help you in that. So this is just a starting point, and I think that's it for this particular session. If anybody has any question, please let me know. Mhm. Yep, everyone's good. No questions.
Yeah, yeah.
Okay. If we are good, then Kira, are you there?
Yes, yeah,
Yes. So
yeah,
yep. So if everybody is good, then we can finish the session then.
yeah, 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 sure.
Mm,
So, please,
Yes, somebody
yeah,
raised
it
hand.
seems,
Yep.
yeah, it seems
Uh,
that it was very clear. Yeah,
Excuse me, I have some
Yeah.
short questions.
Yes,
Like,
please, please.
can you a bit explain when we are going to implement this pruning approach?
The pruning approach.
Yeah, yeah,
Uh, we did not do the pruning yet, but pruning is usually used, for example, like think of it real time gardening. When you are doing gardening, for example, if you are not getting much information, for example, like when I was calculating the information gain, and my information gain was very small, for example, like 0.000001, that information gain is too less. What I have to do is, since that particular division of my data or that particular equation is not able to bring much value to my solution, what we can do is we can set that the important information gain should be at least this way we can prune certain nodes that are not bringing much information. Does that make sense?
yeah,
So several different factors you can use, like minimum leaves that you can set, or things like that you can set, and based on that you would be able to, because I was talking about the feature importance things, right? So feature importance is a very important thing that you can do. So feature importance helps you in feature selection. For example, if you are dealing with a data set which have 60 features, 60 features, which means most maybe some of the features are not bringing as much information. So you can use the feature importance feature from the decision trees or the random forest or things like that, these tree models, and it can tell you that, oh, these features are not bringing as much value, you can drop them, or maybe you can pick the top 10 ones and use them to for the rest of your model, and maybe they would give you so much more better results, faster results, more process, means less processing power you would be used, less memory would be used, and things like that, which means when you are handling or managing so many different features, it would save you cost in that. So feature importance is a very important, you can say, characteristics or property that you can use over here. So pruning is kind of like what gives you advantage in that particular sense as well.
Okay, thank you very much.
Mhm.
Any other question?
Yep. Yep. Miho.
Hi, Salman. Can
Mhm.
you hear me?
Yes, I can hear you.
Thank you very much for the great workshop. Now I understand the algorithm of the decision tree behind the scene. And also, I got the terminology,
Hmm.
clear definition.
Yep, that's good.
Appreciate
That's
it.
good to know.
I have one question.
Sure.
So, if please correct me if I'm wrong.
Hmm.
So decision tree is prone to overfitting.
Absolutely. Yep.
Yeah. So I would like to know why
Hmm.
it's prone to overfitting
Hmm.
from what I have learned today. Which
Hmm.
logic
Hmm.
creates the overfitting
Hmm.
compared to other algorithms?
So the thing is, yes, decision trees are prone to overfitting, and because they are exactly dividing. Means if you don't prune them or if you don't optimize the hyperparameters, then they are gonna definitely learn everything in your data set and would not perform better on the unseen data. So that is why we don't just use decision trees by themselves, are not used as much. They are usually used in a lot of bagging and boosting algorithms
Mhm.
as the base model. So when you use multiple decision trees and you kind of like give them a sample of data, and for example, like if you have thousands of different values, you sample 100 of it, train your decision model on that sample, and maybe you can replace that data back and then sample 100 again, train another decision tree, and make maybe you put a very restricted minimum leaf count or information gain parameter you can adjust, and you can say that, oh, if anybody is not increasing that much information, just remove it, because you don't want it to take a lot of processing power as well. So you can train hundreds of decision trees like that parallelly, and then do the final voting out of those 100, and that gives you better results. That is what happens in the bagging. And similarly in the boosting, what you do is you basically train, first you get the average value, that is your first predictor. Second value is you basically predict the average value and subtract it from the original one, and basically the result of first model improves the result of the next one. It tells you the next one that I made a mistake, this much mistake in the first attempt, please make sure you don't make that mistake again. So next model is going to learn from the previous one, the next model is going to learn from the previous one. So it's kind of like a sequential way of learning. That is what happens in the boosting. So that's why decision trees are very prone to overfitting, but usually majority of the time they're not used alone. They are usually used as a base model for bagging or boosting techniques. Does that answer your
Mhm.
question?
Yeah. Okay. Thank you very much. So that basically in the real world,
Yeah.
the we use random forest instead of just a single tree,
Yeah,
decision
just
tree.
depending on your data set. If your data
Mhm,
set is kind of like big and things like that, or maybe you would have to do hyperparameter tuning as well. But
mhm,
still, decision trees are prone to overfitting way more than. And in that scenario, it is always recommended to maybe just use random forest. Means for me, I always mean decision trees and linear regression or these base
mhm,
models when my data set is pretty simple and I can see the linear relationship coming up or things like that.
mhm,
Obviously, decision tree does not care about any of the assumptions like linear regression and things like that. But still, I usually try them because trying the easiest model, which can be explained really easily, explainability is a very important thing
mhm,
because this way you also learn that which features are important. But
mhm.
random forest or boosting or bagging method, they also tell you the feature importance as well, which means they are also explainable as well. You can figure out which features are have more importance as compared to the other one, and you can focus on them more and things like that. It's always a good idea to try multiple algorithms and see which one gives you results. Hyperparameter tune them, maybe do a voting or some kind of an ensemble of them and things like that. So usually one model, if the data is simple, it would work. But if it most of the time the industry data sets are not straightforward, and decision tree would not be the best model in that scenario. Yeah.
Yeah, okay, thank you very much. But I like a decision tree because it's user friendly and also explainability. Decision
Yep.
tree, can give the great insights to the audiences.
Yep.
Yeah,
Yep.
thank you very much.
Yep. And the thing is, if you understand decision tree, you understand boosting and
Yeah,
bagging techniques as well.
yeah,
Yep.
yeah, yeah, I
Yep.
got it.
It's the
Yeah,
starting point to that. Yeah.
yes, yes. Thank you so much, Salman. Appreciate
Hmm.
it.
Hmm.
Yes, any other question?
Um, Yep. If anybody wants to kind of like step up on that, maybe add all the parameters that I did not add, just like scikit-learn in the model, or maybe try doing it by hand as well. I would definitely recommend it. Means once you do it by hand, then you see how every single formula is being used, and I would definitely recommend that. Yep.
Yeah.
If that is everything, then
Yes.
thank you so much, everyone, for having me.
Thank you. Thank you very much, Salman. I think Amir